Our symposium today. It's on data center lightning protection concepts. A reminder to the audience that we do offer continued education credits for our material, and we will be more than happy to provide certificate information for the attendees today. So thank you very much for joining. And I also include several questions throughout the material to try to keep the audience interactive. And I encourage the participants to use the chat function within the Teams program to go ahead and please enter your thoughts and answers to the various questions that we might discuss during our material. We like to think of lightning protection with a holistic approach. We have a lot going on this particular slide, but really you can overlay this sort of thought process and approach to virtually any application. And here we're showing it's something very much like a data center, but this could be a hospital, it could be any mission critical function where you have a more protected lightning protection zone and with the whole concept of lightning protection displayed here, from air terminals, ground conductors, routing the lightning energy into the soil. You have a grounding system. You have the entrance into the building where they're prescribed lightning protection and surge protection, conveniently colored red and yellow with the DEHN product line for power and information type circuits. But what you see here is a structure where you can provide a more and more protected zone within a particular type of a building, where you see additional grounding and bonding of the structure of the supports, the doorways, wall, any kind of metal structure to build a clean environment. And ultimately, something that might be in a data center server room would be fully protected with multiple layers of protection and grounding and bonding. And there's a lot to see here where things like the shielding of wires and the bonding on one end of a data twisted pair cable might come into play. And what you see here is the application of what's called zones of protection, where you have the outside world that's unprotected, and then with the application of air termination system, you can have an LP zone 0A, which is provided with no protection. 0B is under the protection coverage of the air terminals and mass, the structure itself. And then as you move further into the structure, you can create cleaner and cleaner zones of protection. That's the idea behind using the standards. And much of the industry uses the risk analysis guidelines. And the risk analysis is the start of a lightning protection system. You need to understand what your losses are, what the risk is, what's your tolerable threshold for risk. Are you a hospital full of babies and highly explosive oxygen? Do you have people that cannot be evacuated? Do you have a critical data center infrastructure that has far greater value of the data content than it does of the actual structure itself? So both the IEC and of course the NFPA 780 methods, they start with a risk analysis where you can run a practical calculation and generate a level of risk, which might be viewed as this red bar and the blue bar showing that you're far over the tolerable threshold. And with the application of lightning protection measures, you can reduce your risk to a tolerable level below the threshold. And as a customer, you can select what you feel is a tolerable threshold. So it's an adjustable and dynamic set of calculations. And they're mirrored very similar in the NFPA 780 and XL, which allows you to look at a facility, in this case it's battery energy storage, and analyze what's your risk and apply the proper protection measures. And of course, that comes right out of the standards themselves, both NFPA 780 and the EN and IEC 62305 families of standards. They provide protection measures. And it's what we saw on page 1. It's the air terminals, down conductor systems, the grounding systems, the application of surge protection, shielding, bonding, isolation. And those measures are defined within the standards. And so you'll have NFPA giving you an indication for using UL materials, and you'll have IEC giving you an indication to use IEC approved materials. So there's a lot of very similar aspects to the standards, but there's also several differences between the standards, and gives some advantages with IEC because you get a very rigorous calculation method. You get a very straightforward definition of lightning waveforms so that you can use those in calculations and in further finite element modeling, where you can show a transient event imposed on a building. And you need those numerical models that are provided from IEC. I feel one of the great advantages of the standard itself. There's differences in the approach to lightning protection, but they're very well harmonized. The understanding of lightning protection using conventional Franklin rod designs to have a preferred attachment point for lightning, down conductors, earthing system. Very similar. A lot more similar than there are different between the standards. And much of it is to understand the science of lightning protection. And Dr. Uman from Florida, Gainesville, this is right off the cover of his text on the physics of lightning, and it's lightning versus sycamore tree. And if nothing else, it's a great takeaway to never stand under trees in a lightning storm. They're always prescribed to stay at least 10 feet away from the base of the tree so that you're not subject to such incredible voltages. But there's a lot going on here, and I'd like to draw attention to the lower left, where there's a small lightning step leader that's attaching to the radio antenna on the house. So even though it didn't take the main channel of lightning, there was still a lot of lightning energy that still entered that particular structural circuit. And what you see here is a really great illustration of step leaders, dart leaders, upward tendrils. But the real point is that lightning is thought to move through the atmosphere in steps. And so at some moment, it's a ball of charge over the structure, and it's provoking a spherical electrical field. And everything is under the influence of that charge. And that's why you're seeing so many multiple tendrils attached to this lightning. There isn't one channel that's forming. There's lots of possible channels. And so when the final step leader forms the actual lightning stroke, then you have the full release of charge from the cloud or the ground up to the cloud. A lot of flavors of who's who in the zoo of lightning. This is depicting a downward stroke. There's again a lot of different ways these mechanisms can be presented, but what you get is the science of using that electric rolling sphere, that sphere as a method of calculating where lightning is likely to attach, because we know that it will make that final jump under the influence of the electric field. And so by appropriately applying air terminals, we can create a protected volume. And so here what you have is really just an illustration of that final step leader and that rolling sphere. And there are other great calculation methods. Pardon me. There are other great calculation methods within NFPA 780. We have the rolling sphere method, but we also have things like the air terminal placement, which is using the understanding of lightning, where it will likely attach. And so it's using great body of anecdotal evidence to issue guidelines on where to apply the air terminals for a likely attachment point on a structure. We also have things like the falling angle that can be used with masts, isolated masts, and catenary line type systems, where we can predict the protected volume underneath a tall mast. You often see these at things like grid switching stations and the NASA launch site type applications, where you have a mast that provides a protected volume. The rolling sphere is a fairly sophisticated tool that we can use to really understand where to place air terminals, because it gives you the ability to gauge your risk and then apply the amount, and I'd say the quantity of air terminals to produce an acceptable coverage over your structure. If you have a great deal of risk, you want to account for more of the probable lightning strikes. So you need to account for the small strikes, and the small strikes produce a smaller electric field, which provokes this smaller rolling sphere ball. So that's actually the rolling sphere you would use if you really worried about every single possible lightning strike that could creep into the nooks and crannies on your power plant or data center. You would apply a smaller rolling sphere. And this is one of the things about the IEC methods. It gives you a great deal of flexibility in calculating your coverage model. I like to use this slide to talk a little bit about the actual lightning strike and the numerical models that exist. The mill standards have a great deal of information available to give guidelines on the lightning stroke process and what types of energies you're subjected to in these initial formation of the channel and the long duration types of the strike that have a great deal of energy, but they're not as high they're not a high intensity, but they last a long time. And that's described in the mill standards quite well. But in particular of note is that the IEC strike definition of a 10 by 350 waveform is a fairly close match for the mill standards. And so the IEC methods give you a numerical model to use if you're in the mill standard industry, or you have greater levels of risk that you want to understand, and then you can have great numerical calculation tools. And these other charts are this is a really great example of the lightning strike current during given storms. And this is the distribution that emerges in lightning storms. And it looks just like what you would expect, a natural bell curve kind of performance, where you have a lot of strikes that are in a certain amount of energy. And in this set of data, we have a lot of strikes that are in that 20 kA, maybe range of 20,000 amps of lightning current, but there's still some very high energy outliers that are greater than 50,000 or 100,000 amps. And that's why the bottom graph is very important for us. If you have higher risk, you need to pay attention to more of the spectrum of lightning strokes. So the high risk category, LPL1, pays attention to what I would say the full 99% of any strike that's going to happen, high or low. And if you have less risk, say a typical industrial LPL3, you are certainly paying attention to more than 90% of the lightning strike in the who's who in the zoo of what the strike might be. But really, it's about paying attention to the low level strikes that provoke that small rolling sphere. That's where the highest risk can then be protected. And this slide is just a really great example of just in general terms that you'll see where do surges come from? What is actually happening? This is a great example at a charging station. You can overlay this with the parking lot at your data center, for instance, but you have direct strikes. You have things that hit directly to your structure, and they can cause, of course, obliterate damage. You can blow up your charging stations. You can blow up the light poles in the parking lot. You have indirect, and this accounts for far more of the areas around a structure like a data center. You've got all the surrounding areas within hundreds of yards, even miles away, where if the lightning strikes the ground, it's got to make it to ground somehow, right? That is the nature of lightning. It is striking the ground. The closer that is, you have more and different effects from the indirect. And this, you would think of this as like the ground potential rise around your structure. And then, of course, electrical sources of surge. And this goes from everything from the grid, from brownouts to grid switching to going on to backup sources within a data center where you're going to a motor generator, a diesel generator, or perhaps you're going off of different battery sources. This is, of course, huge in data center space where you're almost always on what would be a continuous inverter type source where it's always a battery source. And then you switch in your different sources that keep the batteries charged. But all those families of surges, because you've got a lot of sources of power at a particular data center, the grounding of those sources becomes a real issue where if not enough attention is paid at the design and installation during a surge event, it'll really emerge as a problem. We worked, of course, directly with the other industry standards bodies, third-party inspections. I like this slide because it basically gives the data center space a third-party certification process. There's others available from ETL. This is interesting to note that the UL will also give you a master label inspection services on the IEC 62305 type lightning protection systems. So I'd like to invite the attendees to give us your thoughts. Always interested in improving our material and making sure that we're striking topics of interest for the audience. Why are you attending our lightning webinar today? You're looking for information? Always happy to help with that. Several different answers. Are you bored? I would consider this a very interesting topic. So this gives a lot of should provoke a lot of thought. Please enter what you might have as a guiding reason why you were interested in our webinar today. Thank you. Give everybody a moment to enter an answer. We'll take this afterwards, and we try to use this to improve our systems and our presentation. So the data center world is rapidly adopting lithium-ion battery technology, and for any number of reasons you see in the data sheets for lithium-ion, you have great advantages, which are leading to a very high rate of adoption in the industry. It's upwards. There's great reports that upwards of 38% of data centers globally would be using lithium-ion battery over lead-acid type battery systems for the advantages they offer. But they offer a greater fire risk as well. And the equation is 4 lithiums plus an O2 gives you a couple of lithium dilithium oxides and a lot of heat. And these are just some of the images available online where you can see the experiment where they poke a phone battery. Now imagine that at a scale that's running a data center. And now you have a real issue to address. It's the prevention of fire in a battery system. And this is exactly the point of the NFPA 780 and IEC 62305 lightning protection systems. Eliminate lightning as a source of that ignition. So what's the biggest loss to a data center from fire? I'm actually very interested in what the industry thinks of this. Is it the lost revenue from the cloud services? Is it public image being tarnished? Nothing, the people that are very proud of their branding don't want to be in the news losing a data center to a lightning strike fire. Is it the environmental pollution itself? We talk a little bit about that lithium-ion battery risk. virtually can't put that fire out. You got to let them burn. That's a horrible consequence. Customer loss, IT employees. That's a big deal. Interested in what our audience thinks the biggest source of loss is, so that again we can help address what the industry needs to see. I've got another question. What functional area of the data center must be protected from lightning and induced ground potential rise? What's actually the victim? Is it the main incoming feed, backup generators, transfer switch, battery plants, the fire extinguishing control systems? Is it the chiller that keeps the data center cool so it doesn't melt down? Do you have to protect the isolated ground racks? Well, I think the answer is all of this stuff. There are no wrong answers here. It's everything. But what's the real risk that you have in your plants? So early on, I like to address another topic that's very well described in the IEC 62305 standards, is bonded as opposed to isolated lightning protection systems. And in a data center environment, there's a lot of good reasons to consider an isolated system. And we've done some modeling, and this is just a very simplified sort of diagram, but this physical model can be developed into a mathematical representation using tools like XGS or PSpice, and you can induce the transient, and it's the lightning stroke that's defined by IEC. And when you induce that transient, you can see where the energy would otherwise go. And the point of this type of research is to look at and compare a bonded system to an isolated system. And in a bonded system, you would think of it as a bird on a wire. Everybody goes up together, everybody's down. There's no voltage differences. It's equipotential bonded. The idea is that if the lightning strikes the building, it doesn't produce sparks and flashover to the other metal bodies within the structure. But what it does do is share some of that lightning current into the electrical grounding system, directly into the grounding, which can then influence the electrical works within a structure. It's very hard to see on the dark graph. Sorry about that. But here you can see the red line. That's the lightning current in an isolated system being diverted away from your internal electrical system. So you can provoke lightning directly into your bonding system, or you can isolate from it. And some users of lightning protection systems vastly prefer isolating from it and not letting it bond into your system. Like an electrical switch yard, the masts are set up around the transformers so it diverts the lightning energy into the ground, not into the metal frames of the transformers. So we've done some numerical studies. There's a lot of discussion points on that. Have a polling question I'd like to ask the audience and the attendees. How does lightning induce surges? Are these direct couple of the strike into the wire? Does it directly couple into the wire? Is it electromagnetic induced current from the plasma channel into the adjacent through magnetic coupling? Maybe it's ground potential rise provoking a voltage between the wires to ground, and that drives the surge. So there's a lot of chicken and the egg. Is it current being induced? Is it voltage being induced? Is it both? Well, the answer is anything and everything. So there's things you can do about each of these mechanisms. And so lightning protection involves addressing each of these mechanisms to reduce the overall effects. So air terminal placement and rolling sphere illustrations. This is a data center that had a couple of key things. You've got some solar collectors on the roof. You've got a lot of chargers. You've got other structures up on the roof of the building, and the idea is to produce that canopy appearance. It's the rolling sphere coverage over the building. It's the equivalent electric field that would otherwise be present from a lightning strike. So if the charge is momentarily floating over the building, about to form the final channel, it will influence the air terminal first and strike the air terminal. And it's really about just getting that little bit closer to the lightning strike to try to give it a preferred attachment. The lightning tends to want to hit corners and things already. So if you can get your air terminals up and around those cornice areas, the corners, structures, the high points, give it a preferred attachment point. And you may also need to take into consideration things like the lamp poles out in the parking lot. These are now inducing lightning strikes into the lamp, into the luminaire, directly into your electrical circuits. Now you've brought the lightning directly into your electrical service panels from the outside through the light pole. And this is where the application of proper air terminals on the light poles, surge protection at the luminaires would reduce the energy that's brought back in through the back door, as it might look. Things like cameras, things like card readers out in the gate control areas, where the gate controller is a direct path back to the security system inside the structure. So the application of lightning protection, electrical surge protection, grounding and bonding produces a much more resilient, thorough system. And this is a great sketch that sort of shows that lightning ball rolling over a structure and what you would expect from the application of proper air terminals over that parking lot and the building itself. And it lets you distinguish between the unprotected world and the protected zone B underneath the canopy of protection. So flashover is a very serious problem with lightning protection, in that if you cannot separate from it through calculating the distance between the down conductor and adjacent electrical circuits, you either bond it or you separate from it. And one of the problems with an electrical wire in your house, you can't bond that because it's an electrical power. It's maybe a window frame or the flashing on around a window jamb. You can ground and bond and keep that from arcing, and that prevents that flashover. But you can't bond your electrical circuit so that you have a high voltage that could build up and flash to the camera or electrical circuit. So these are just some illustrations that show how extreme this problem can be, that flashover from the lightning protection system inadvertently flashing into your electrical circuits. And this is a source of that culprit, where you have a down conductor and it's near the electrical systems and it's close enough to flash. So the typical standards would tell you to bond to it. But you can see just here alone, you can't really bond. There's nothing to bond. It's electrical plastic stuff, but it's going to flash to the wires. And you can even see some discoloration where it may have done that in the past around these circuits. Got a grounding question. This is a great topic for lightning protection, but in the world of experience, how far apart should a typical 10-foot deep earth rod be spaced? How far apart do you have to keep your earth rods for them to maintain effective dispersion of energy into the soil? Well, it turns out it's the best rule of thumb is twice the depth of the rod apart. So that two 10-foot rods would be 20 feet apart. And that gives it a space within the soil for the charge to disperse. And that's really the point, is to design an effective grounding system. And this is why you want to pay attention to the standards and install electrical grounding that meets the needs of lightning protection. If you only pay attention to the National Electric Code, Article 250, you will meet the National Electric Code. You can operate safe electrical power. That's great. And I always start with Article 250, except when you apply lightning protection, you need more. You need to pay attention to more attributes of grounding. You need ground connections at all the downcomers around the building. And it leads you to certain types of designs. And within IEC, you have the choices of individual, what's called a type A, which is an individual ground rod at each of these down conductors to assure that the lightning energy is properly dispersed. And depending on your risk, you can design this system with the adequate electrical ground rod in contact with the soil. Great alternative is a type B, and this is also very commonly seen in NFPA 780. It's a ring around the structure, and sometimes it's embedded within the foundation. And when that's done, you have to be very careful that it's done correctly, that it's properly bonded in with the rebar. But this is an acceptable type of a grounding system. And what's important to see is that there's either a ring or maybe what's called a type A, this radial, and you might consider it an isolated rod. It's on its own, but it's connected to its down conductor system. And this leads you to a much larger discussion of things like grounding and bonding and bus bars within a structure. I'm sure we all have great examples of seeing red hot connections on a grounding bar where neutral currents and grounding currents are the AC power are being inadequately bonded and grounded together correctly. There's a couple things I like personally about an image like this, things like the two-hole lugs that prevent them rotating and coming loose over time quite as easily. Things like the conduit you have a clear conduit connections that all the metal components are also bonded in with your grounding system. So these are just a few images that we look for and that are important in the aspects. And then, of course, there's a whole greater topic of soil resistivity and testing and connections with your validating your lightning protection system is adequately connected to the soil earthing electrode. Understanding soil resistivity versus the risk that you have. That's what this chart in the upper right is. It tells you if you've calculated your risk of lightning to be very high, then you need more metal electrode in contact with the soil for a given soil resistivity. So if you have very poor soil, you need more conductor in contact. And this is where understanding your soil, understanding your risk, and really doing a vigorous mathematical set of calculations can really help guide the designers to make sure they've designed a robust system for lightning protection. So here's a question about conductor separation. From what type of equipment should down conductor separation be maintained? You've got a down conductor coming down the building. What do you need to keep it away from? In this case, it's not a trick question. It's all of these, but you want to stay away from the neighboring buildings, the trees, conductive parts around the windows and frames, the roof mounted structures, interior installations. So if you're intentionally separating, you need to stay away from all these types of items and really understand what's around you. There's a great set of tools within IEC and within NFPA 780 that allow bonding distance, and which is also similar, called separation distance, to be calculated. So you know at any given height around a building what you need to stay away from and what are your limits. So if you're up on the roof, you can calculate that anything within 50 or 52 centimeters in this particular calculation has to be bonded. So if you cannot separate, you have to bond. And what that looks like is something that you might see up on a roof, where you have conductors routed around the roof, and this is a typical bonded system, but there's some things that weren't separated enough, and they should have been bonded. And if you can't separate from it, you need to bond. And so here you see a case where there might be some sensors that we're trying to stay away from, but failed in the actual, the installation of the air terminal. You can see is actually too close to something that we might have wanted to stay away from. And that leads to a whole class of materials that actually provide isolated lightning protection systems. So you can install air terminals to avoid side flash. You can stay physically away, or you can use isolated and insulated type materials that will provide a suitable lightning protection system. And here's a set of light air terminals placed over, in this case, it's a hospital, and you can see it's going to have the very high levels of risk, very, very similar to what we would see in other industries like data center industries. These are some images from a data center chilling station, and you can see the application of insulated and isolated air terminals around the chillers to prevent strikes into the chiller, to protect the chiller itself, but also protect the integrity of the entire electrical system by keeping the lightning out of the structure in the first place. There's a lot of things to consider in a structure such as this. You've got a large cosmetic facade that's set up over and around the chillers. And so here it's going to be virtually impossible to insulate or isolate from the chiller itself, because all of this massively bonded steel up on the structure. So here is a great example where you have to use a bonded system because of the structure itself. It's going to lead you into a application path that's most suitable for the types of structures you're going to see, because in this case, exactly that, it's a cosmetic facade to hide the chillers. And here's a couple of great slides that just talk about the basics again: the lightning protection, equipotential bonding, and how that influences the application of metal rebar bonding systems, the buried earthing systems that are within the structure. And these are opportunities to build an extremely robust equipotential bonded system that will give you the most cleanest environment and the best reduction of risk. So nothing replaces boots on the ground. Looking at site conditions, this was a walkthrough at a data center, and we observed broken pigtails, broken ground connections, single hole bolts that may have come loose on themselves. Here you see a lot of red flags. There's things like the copper cable, although it looks very, very robust, it's directly embedded in the concrete without a suitable insulated plastic conduit or covering for the where the water and the concrete and the copper all mix with oxygen. That's going to be a very key area where it's going to erode over time and lead to exactly this, a broken grounding connection. Here's a couple images of a plate electrode, where it's a large surface area copper plate. And in this case, it's connected to the down conductor in what we might call a type A system. So to the left, you see something that's probably a buried ring. The bonding connections are possibly broken, but there's a buried ring there. And here you see something that's like an isolated type A system. And these are just examples of what to look for, what you see in a data center type application, where the conductors come down off the structure. You can see the application of an isolated type down conductor connected to the grounding system. These are some great illustrations showing, practical applications where on portions of the building, they're already sealed up with concrete, and you can't get to an existing structure. And this is becoming, of course, very common in the industry, is to take an existing building and repurpose it as a data center. But what you find is that it's not a perfect world, and that maybe the grounding system isn't accessible. Maybe there's a buried ring that you just can't get to. So the lightning protection system has to be adapted with suitable connections and the suitable number and a very clear and distributed route into the soil to reduce the risk of fire and side flash. Here's a nice image of what you might see if you had that rolling sphere electric eye, and some note that to be very careful that it's a lightning protection system, that there are risks associated with standing right there next to that lightning down conductor. Here's a couple images showing the application of an isolated lightning protection system on a data center where the customer did not want lightning currents injected into the structure. They have gone to great lengths to build a clean data center, and the last thing they need is lightning energies directed into a buried, concealed earthing system, which is very difficult to trace where it's going to flash over inside the structure. But the application of lightning protection around the structure isn't enough. You still have to pay a great deal of attention to surge protection devices, to the electrical protection around things like transfer switches at secondary and tertiary load center panels that might be feeding the lamps out in the luminaires out in the parking lot. You want to prevent that energy from coming back into the circuit. You want to have lightning protection and surge protection embedded around the battery backup systems and your inverter converter systems. So it's not just that you applied a single SPD at the service entrance. It's about looking at the whole system and really applying surge protection to produce the cleanest environment at the point of use. So this would look exactly like the image we saw in the very first parts of our slides, where you're creating a cleaner and cleaner environment as you move into the electrical distribution system. Very similar application here, where you have dual sources, motor generators, transfer switches, and the application of surge protection to get a very clean, resilient structure, so that you have it at the service entrance and, of course, after the transfer switches, so that the victim is always protected. And this is what it might come to look like in a physical structure, where you have a very robust grounding system with electrical surge protection applied at key areas around the plant on both the electrical power and the data that's controlling things, as we mentioned before, thermal sensors, temperature, fire alarm sensors, intrusion alarms, access alarms around doors, and so the security systems that are all very integral and really part of a secure data system infrastructure. Hybrid power systems, trying to get some advantage of solar array and DC fed battery systems in a structure, and the application of air terminals and grounding measures for these systems that are being added into legacy structures, where you still have to pay a great deal of attention and not miss the opportunity to create a more robust structure. Data center protection, where to protect: mains, distribution panels, backup systems, chillers, DC power feeds, all the low voltage control systems. You could almost use this as a checklist, as an inspection list for your own maintenance plans, and go through the structure and really pay attention to the application of surge protection devices. Are the devices working? Are they in good condition? Have they suffered failure or loss? After every type of lightning type storm event, you may want to conduct a maintenance type inspection and make sure that the surge protection is still doing its job. The SPDs need to be installed directly at emergency systems. This is right out of the National Electric Code 70, and it's that anything that is considered a emergency or life safety system also has to have surge protection installed directly at those fire and control panels. And this is a discussion point that I like to talk about with customers for the application of things like data circuits, twisted pair circuits that are running around a structure or between structures. And this is very critical on something that you might see like at an access gate out in the parking lot, where it's a structure that's physically removed from the data center and probably even on its separate grounding system. Where do you bond and isolate the shield? It's always in the world of shielding, it's always prescribed to lift one end. You don't want to bond the shield to earth at both ends. This creates a loop, especially in a separate grounding field, and this would be catastrophic for noise and problems. So you lift one end, usually at the remote end, and maybe at the gate structure. But what's important about this illustration is that extra little gas discharge tube that's installed on the lifted end. One end you can see is direct earthing. The other end is indirect. And think of it like a pressure valve on your water heater. As that voltage builds up on the end of that cable, eventually you want it to release. And that's what that gas discharge tube, it gives it a pressure release and then goes back to an isolated system. So it's indirectly bonded. It's a really great way to improve your signal integrity. This is just an example of a redacted master label. This was a data center. The customer was very interested in having third-party compliance, and DEHN is deeply involved with the inspection agencies and can help with these process. And this is just another application of an isolated system. The people at Launch Complex 40 down at Cape Canaveral, Florida, are very concerned that their lightning protection system, which is in this case an array of masts with catenary wires strung around it to produce an isolated system that prevents any of the lightning energy from being induced into the launch vehicle that has a very high value, that has full of liquid oxygen and liquid hydrogen, very explosive, high risk area, and the application of an isolated lightning protection system for them is unquestionable. So just some of the topics we covered today, we wanted to just make sure we looked at, what are the central issues with data centers for fire protection and content protection? What is the nature of lightning, and how do we best deal with the mechanisms of lightning? Look at the electric field and how it provokes step leaders. What that means in the world of lightning is how you deal with it to adequately reduce your risk. And that leads you to the pillars of lightning protection, the air terminals, down conductor systems, separation, bonding, surge protection devices. This is what addresses all the mechanisms and adequately protects a system and produces the lowest risk application.